Hello viewers, welcome back to the course on matrix computation and its application. So, today we are going to start with the another topic, that is the four subspaces that are connected with the linear algebra. So, let us discuss that one. So, the today's topic is about the four subspaces. So, today we are going to deal with the matrix, a matrix of order m cross n. So, how we can find out the subspaces, four subspaces are related to this matrix. So, before that we just want to discuss one function that is called the linear functions. So, a function f that maps position in the domain D to the points in some t is there. So, I am defining the map f from some domain D to the set t. If this is going from D to real number, then I can say t is a set of real numbers, or if it is a complex number or whatever it is. So, we are mapping the function f from the domain D to the codomain, that is t. So, a function f that maps position in the domain D to the point t is said to be linear function whenever f satisfy the following conditions. The first one is that if I take the function f of the addition of two numbers from the domain x plus y, then it should be the sum of their images. So, it should be equal to fx plus fy, and if I take the scalar multiple alpha times x and then I taking the map of that one, so that should be equal to the scalar multiple of that, the image of that under the function f for every x and y belongs to D. So, this is type of functions are called linear functions. So, this type of functions if you see from here, then looking at this type of function, you can also remember the definition of the subspaces, because in the case of subspaces, we also have to satisfy two conditions. What is the vector addition, and another is the scalar multiplication. These two, and here also if you see it, it is also type of vector addition we are doing. So, instead of vectors we are dealing with x and y that is coming from the domain, and this is also the scalar multiple. So, we can have some relations between the linear function and the subspaces. So, for example, I just take one example that how the linear functions will be look like. I can define the function f maybe from r square to r, or maybe I can define the function f x1 x2 is equal to x1 plus x2. So, in this case I just want to see whether it is a linear function or not. Then if you take f, so this is I am taking the function here. So, let we take x and y belongs to r square, then x will be written like this one, y is equal to y1 y2, now I can take the linear combination x plus y, so that can be written as x1 plus y1 x2 plus y2. Now, I take the function f of x plus y, so it will be equal to f of x1 plus y1 x2 plus y2, and this is equal to given here. So, from here I can write as x1 plus y1 plus x2 plus y2, and this can be written as x1 plus x2 because it is coming from the real number, and y1 plus y2, and this is also equal to x1 x2 plus f y1 y2, and that is equal to f of x plus f of y. So, this is true for all x y. So, true for all x y belongs to the domain R square. So, this is now from here you can check that this is satisfied. So, this is the first one we are doing. Then the second one I can take f of alpha x. So, it can be written as f of alpha x, and x I am taking here this. So, it can be written as alpha x1 x2. So, it can be alpha x1 alpha x2, and this is equal to, according to the transformation, I am taking alpha x1 plus alpha x2, and from here I can say that alpha is x1 plus x2, and this is I can write as alpha f of x1 x2, and that is equal to alpha f of x. So, second property is also satisfied. So, from here I can say that the mapping, whatever the mapping we have defined from x x1 x2, that is equal to so this is I can write as x1 x2 x1 plus x2 is a linear function or map. We also call it map. So, this is a linear functions or a map we can define. Now, so from here now we define the definition subspaces and linear functions. So, now we want to find the relation between these two. So, for a linear function f mapping from Rn to Rm. So, now we are talking about the matrix A that is of type m cross n. So, let Rf denote the range of the function f. So, Rf basically is set of all the images fx such that x belongs to Rn, and we know that this will be the subset of r raised to power Rm, because that is the functions coming to this one. So, for example, I take a matrix A. Suppose I take a matrix like this one, 1 1 2 and 2 1 3. So, suppose I have taken this matrix, this is 2 cross 3 matrix. Now, if I take the transformation using this matrix, then definitely I want to calculate what is the Ax. So, A is here 1 1 2 and 2 1 3, and I will taking a vector applying on this one. So, it is 2 cross 3. So, it should be 3 cross 1. So, suppose I am applying it on the x1 x2 x3. So, that is 3 cross 1. So, from here if you see this one, I will get here x1 plus x2 plus 2x3, 2x1 plus x2 plus 3x3. So, this is a vector I am getting. So, and this vector is 2 cross 1. So, this is a matrix from of order 2 cross 3, and I am taking the vector x coming from R3, and then the image is going to R square. So, I can say that this A represent a transformation that is from R3 to R2. So, R3 means the triplet I am taking, and so that is coming from R3 to R2. So, I am taking the vector from R3 that is coming from the domain. So, this is my domain here. I can say there is a domain, and then the image is going to the R2. So, this is the mapping we are basically applying here. So, this is what we have written. So, we have defined that for a linear function f mapping Rn to Rm, let range f denote the range of Rf is the range of the function f, that is given by this one. So, then we have the theorem that the range of every linear function f from Rn to Rm is a subspace of Rm, and every subspace of Rm is the range of the some linear function. It means that if I take a map f from Rn to Rm, actually sometime we also represent R like this one. So, this is same equivalent. So, we have a linear function from Rn to Rm. So, it says that the range of f that will be is a subspace of Rm, and in this case that if S is any subspace of Rm, then it is the range of some linear functions. So, this is the definition here. We have defined the theorem, and now we want to prove this theorem. So, let us start doing this one. So, the first one. So, the first one says that we have a map from Rn to Rm. So, this is same as I have showed the matrix of the order m cross n, because whenever we deal with the vector spaces having the dimension more than 1, that is like a Rn to Rm, and we want to, if we want to show the linear function, then that come across the matrix. So, that we will discuss in the future, but just now I am defining a map that can be also written in the form of the matrix A m cross n. So, I am writing this the function f. Now, so Rf the set of all the images such that x belongs to Rn. Okay, and definitely we know that this is a subset of Rm, because if I take any element from the domain applying the function f, then it will go to here. So, it is a subset of Rm. Now, let we have, so now we want to show that this Rf is a subspace of Rm. So, for this one we need to satisfy two conditions, vector addition and scalar multiplication. So, now we have to satisfy the two conditions for subspaces. So, the first one is that vector addition. So, let we take y1 and y2 some belongs to Rm. So, I am taking two elements from the range set Rm, not from Rm, I just take from Rf. Then there exist some say x1 and x2 such that f of x1 is equal to y1 and f of x2 is equal to y2, because I am taking two elements, that is distinct elements from the range space. So, if it is in the range space, then definitely there will be some x1 and x2 from Rn such that fx1 is equal to y1 and fx2 is equal to y2. So, this x1 and x2 is coming from the domain that is Rn. Now, y1 plus y2. So, this I want to see that where this will lie. So, this can be written as f x1 plus f x2, and this can be written as f of x1 plus x2, because f is a linear map. So, it is a linear map or linear function. So, this is the property of the linear map, and now from here x1 plus x2 belongs to the domain, because x1 we are taking from the domain, x2 is we are taking from the domain. So, and f is applying from the Rn. So, it is a domain. So, now from here I can say that, which implies that y1 plus y2 also belongs to the range of f, because it is coming as a function applying on Rn, and definitely its image are y1 plus y2, and it should be from the range space. So, it shows that y1 plus y2 also belongs to the range space. Also, if I take for any scalar alpha, so this is I am taking the scalar alpha, alpha y1 can be written as alpha y1 I can write as a x1, and since it is a linear map I can write as a alpha x1. So, which implies that alpha y1 also belongs to the range space of function f. Okay, so, from here the scalar multiplication of y1 is also belongs to the range space of f. So, from here we can say that the two properties, vector addition and scalar multiplication, are satisfied, which imply that the range space of f is a subspace Rm, and Rm we already know that it is a vector space. So, here we know that Rn and Rm are vector spaces, that we already know. So, range space of f is a subset of Rm, and then we also showed that it also satisfies vector addition and scalar multiplication. So, it is a subspace of Rm. So, the first one is satisfied. Conversely, second one is, because we have to show that the range of every linear function is a subspace of Rm. So, that we have shown. Now, we have to show that every subspace of Rm is the range of sublinear function. So, this one we want to show. Now, we need to show that any subspace, say S in this case, of Rm is a range of some linear function. So, this one we want to discuss. Now, for this one, let S is a subspace of Rm. So, this one we have just defined. Now, the F is a map from Rn to Rm. So, that we already know. Suppose S is equal to span of V1, V2, Vn, because S is a subspace of Rm. So, I know that it can be spanned with the vectors. So, say I have taken V1, V2 up to Vn. So, these vectors are spanning the whole subspace S. So, I can write that S. So, if it is span of this, then I can say that S is equivalent to the linear combination alpha 1 V1 plus alpha 2 V2 alpha n Vn. So, it is set of all the linear combination of this one, where alpha 1, alpha 2, alpha n are scalars. Now, now let us construct a matrix. So, I construct a matrix, say A. So, let us construct a matrix A. So, what I am doing is that putting column vector as this V1, V2 up to Vn. Now, I have taken the n number of vectors V1, V2, Vn. So, I am putting this one as the columns of the matrix, this one. So, now from here you can see that this is n number of vectors. So, it has the n number of columns, and in this case it is coming from the Rm. So, it has the component m components. Each of the vector V1 has a m component. So, you from here you can see that this will be a matrix of order m cross n. So, I have taken the n number of vectors that we are taking, that it is spanning the S, that is the subspace of Rm, and that each of the vector has a m number of component. So, from here I can write like this one. Now, so this now the linear combination as given above, that is in 1, we can construct a vector that is alpha 1, alpha 2, alpha n transpose, it means the column vector. So, that belongs to R n cross 1. It means it has a n number of component, and cross 1 means it is a column vector. So, this I am writing. Then what I could do, I will write A into, so this I call it alpha. So, A alpha. So, it become V1, V2, Vn, and alpha is alpha 1, alpha 2, alpha n. Now, I have taken the alpha from the Rn. So, this is containing the n number of component, and this is the matrix A. Now, from here this one, if I, so it is a matrix of order m cross n, and this is n cross 1, and now we can multiply. So, from here you can see that this will become alpha 1 V1 plus alpha 2 V2, and I can write alpha n Vn. So, this one I am getting from the right hand side by multiplying this vector with this matrix, and this can be written as alpha 1 V1 and alpha 2 V2. But what is this alpha 1 V1 and alpha 1? It is a linear combination of V1, V2, V3, and that is coming from the S. So, basically if you take from this is equal to S. So, from here I can say that, so the function I am taking function f(x) is equal to ax is linear because f x plus y can be written as a x plus y, and this we can write as ax plus ay, and that is f(x) plus fy. So, I have taken this transformation as ax as a linear function. So, in this case it is satisfying this one, and also f of alpha x, it can be written as alpha ax because it is just a scalar I can take around on the left hand side, and that becomes fx. So, it is a linear function. So, from here I can say that the range space of my f in this case is set of all ax such that x belongs to R n cross 1. N cross 1, whenever we write that it is a column space. So, x belongs to R n cross 1, it means x is a column vector, and this is become complete S. So, that shows, so which implies that for any subspace S of Rm, there exists a linear function, that is ax in this case, such that a range of that linear function f x is equal to ax is equal to the S. So, this is the proof of the theorem. Now, the same thing, so we have discussed this thing. Similarly, we can discuss about A transpose. So, if I take the A transpose and then I can define the range space of A transform. So, what is going to be there? Now, if my A is m cross n, then we know that A transpose will be matrix that will be, suppose it is matrix B, so it is n cross n. So, m cross n, that is n cross n. So, in this case I can say that the range space of A transpose is set of all. Now, we have to take A transpose y. Suppose I take the y, and y in this case is coming from Rm. So, this will belongs to Rn. Okay, so, I can say from the range space of this is the set of all A transpose y such that y belongs to Rn. Okay, so, we have discussed the range space of matrix A, and so just now we have discussed that we have defined the linear map from Rn to Rm, and then we have defined the range space of F. Okay, so, from here now after that, using this one we have shown that for any linear map from Rn to Rm, there is a matrix involved, that is A, such that we can have a linear transformation for each of the subspace of S, this one. So, now from here I have shown that if we define the linear transformation with a matrix, then we can also have the range space of RT. So, this is the definition we have taken for the range space of AT, that is taking the transformation of matrix A, that is the transpose, and putting the vector y, applying on the y. So, that is the range space of A transpose where y is coming from R, and definitely this is subset of R. So, it is just the converse of this one. So, these things will, so let me stop today here. So, today we have started with 4 subspaces. So, in that case we have discussed the linear function, and then we have discussed that how the linear function can be represented by the matrix, and we have discussed about the theorem related to that one. So, in the next lecture we will continue with this one. So, thanks for watching, thanks very much.